at the top in your warm-up. So just practicing all of those different types of equations that we solved this week, last week. I don't know. What day is it? It's Tuesday. So that would have been last week. Okay. All right. What about the first one? What strategy you want to employ to find the solution to that equation? All right. Let's put the two logarithms together. So if we do that, because they're addition, we would multiply. What about on that other side? Yeah, take the exponent up, so 2 to the third. All right. Now that we have single logarithms, we can set everything inside of those logarithms equal. So x minus 3 times x plus 4 would equal 2 to the third. Oh, wow, what did I just do right there? Undo. Okay, so, fun times. If we multiply all that out, x squared plus x minus 12 is going to equal 8. Right? Move some things around. X squared plus x minus 20. Oh, that's going to factor nicely. Plus 5 minus 4. And so we have x equal to negative 5 and x equal to positive 4. Now, we started with a logarithmic equation, and when we start with a logarithmic equation, it is essential that we check our solutions, make sure they still work, okay? If I put negative 5 inside that first parenthesis, are we good or no? No. Negative 5 minus 3 is a negative number. No negatives inside a logarithm, so that one is extraneous. All right. Let's try 4. 4 minus 3? Yes. That's good. 4 plus 4? That's good. So one solution. Okay. What about B? There's way too many letters and not enough numbers, as people like to say. Yeah, let's just move it all to one side. All right, let's start there at least. Put some things together. So if we do that, if I move 2 e to the x and I move 6, that's going to give me e to the 2x minus 4 e to the x minus 5 is equal to 0. All right. 3 terms there. If we're lucky, it might be quadratic in nature. We could factor it like we would a trinomial. All right. What would I multiply together to get e to the 2x? E to the x and e to the x, because we would add the exponents. Okay, that matches for that middle term, so we're good. And let's figure out the factors we need. What would multiply to negative 5 but add to negative 4? Negative 5 and positive 1. Okay, good job. So there's that exponential equation in quadratic form, right? We're going to set both of those equal to 0, so we would have e to the x equals positive 5 and e to the x equals negative 1. Okay. How would I solve e to the x equals 5? We do a logarithm, okay? We put it in logarithm form. So the base is e. I would use an ln. It's going to equal my exponent, which is x, and the 5 goes inside, okay? What about e to the x equals negative 1? You can't do it, right? That's an extraneous solution, all right? You can't do that, all right? Because if I wrote it in logarithmic form, I'd have the natural log of negative 1, which we know is undefined. Okay, so just one solution right there, right? Better than the first time you saw that? Yes, sir.
Why don't you figure out the ln of 5?
Like get a decimal approximation? Because we like to deal with exacts and absolutes. So why do an extra step when that's an exact solution? All right. If I was doing a word problem, let's say, that was talking about, feet. I have no idea how many feet ln of 5 is. That's when a decimal approximation is appropriate. Okay? Otherwise, if it's just pure mathematics, leave it. Okay? All right, what about this one? Log base x of 3 plus log base x of 12 equals 2. A little different place than we've seen an x before, but still no different. Okay, what do you think? I can't put them together, right? Because they have the same base. It's a base of x, and they're being added. So we could write that as log base x of 3 times 12 is equal to 2, or log base x of 36 is equal to 2. Okay. Just like we do when we're solving any other equation, it's logarithm. A single log equals a number. Let's just write it exponential form. What would be my base? X to what power? Second equals 36. What's x going to equal? 6. Okay. Now, typically when we solve that equation, we'd get how many solutions? If I took the square root of both sides, how many solutions would I get? 2. Okay. But can the base of a logarithm be negative? No. So that's why we only need that positive 6. Okay. I liked that one. I hadn't seen one where they'd put the x in the base before, so I thought that was a good one for us to look at. Okay. So questions on those 3? All right. Just like to give you some more practice on all of that. All right. Well, let's jump in here and get to today's lesson. I'm excited. The more I mess with it, the more I like it. All right. So we're going to talk today about something called a semi-log plot. And as I said before, it was something I had never seen until I went to training this summer. Probably could have seen it in a stats class, but I didn't see it I took business statistics in one summer because they quit offering the math statistics so that I could graduate on time. So schools will do that. So Dr. Cho, he was awesome. Okay. He had a massive heart attack driving through in Atlanta and lived. That's all I have to say about him. His hands were as big as your face. I've never met such a massive man in my entire life. Okay, and he almost knocked me down the stairs one day, but it's okay. He smoked like a freight train. You walked into his office, you literally had to part the smoke like a curtain and walk in to ask a question. Anyway, that was 1996, just so you know. Okay, so our learning targets today: determine if an exponential model is appropriate by examining a semi-log plot of a data set, and then construct the linearization of exponential data. So I left you this paragraph here because I thought it was kind of interesting, all right, is that we use logarithms a lot when we deal with exponential data. And I want you to look at these 2 graphs, okay? This is the same data, all right, on 2 different types of graph paper, so to speak. The first one's on our typical graph paper, where x increases equally, y increases equally, incrementally, like it's beautiful. And when we see this exponential function, we've got some really crazy numbers that we can't really match until x gets a lot bigger, right? So I can't tell what this 40 is really on, okay? It's somewhere between 0 and 1,000,000. All right, well, that doesn't help me a whole lot, okay? That doesn't help me. But I get out here to 140, and I'm like, oh, I'm getting closer to 2 million now. I can see that a little better, okay? So one of the things that they will do is to take those y values, and they'll take the log of all the y values. And then they change the y-axis, okay, to a base 10 type axis. So this is 10 to the first, which would be what? 10 to the second, which would be 100, 10 to the third, 1,000, and so on, okay? And the reason they do that, they keep the x's the same, is so that we can see the data a little bit better, okay? We can see which actual numbers we're talking about a little bit nicer, okay? This is called a logarithmic scale, okay? Now, which means between 10 and 100, all right, I've got to get all the numbers between 10 and 100, all right? So somebody in all their infinite wisdom, I don't know who they are, okay, said, well, this is what we're going to do. We're going to change this scale, all right? And we're going to come back and fill in that box in just a second. We're going to change this scale for a second, all right? So I want to show you 2 versions of this graph paper, all right? The first one where I have 1, well, that's really 10 to the 0. Okay, where I have 10, that's 10 to the first. Where I have 100, that's 10 to the second. Okay, and where I have 1,000, that's 10 to the third. Okay. Now, what's even cooler, I think, are the increments in between. All right, because everything is in base 10. By that I mean the first line after 1 is 2. That makes sense. The next line is 3, then 4, and so on until you get to 10. Okay? Anybody want to guess what the first line after 10 is? It's 20, because I got 10 spaces to get from 10 to 100. Okay? So this is 20, then 30. All right? When I get to 100, what do you think the next line is? 200, because I got to get to 1,000. All right? So it's all base 10. All right? It's really a weird kind of graph paper. Okay? The same is true over on the other side, okay, for the different ones, except this time they just labeled it 10 to the first, 10 to the second, 10 to the third, and so on. But each individual line on that y-axis goes up by that base of 10, okay? So from 1 to 10, it counts by ones. From 10 to 100, it counts by tens. From 100 to 1,000, it counts by hundreds, all right? Weird, but it is. That's all it really is, okay? Now, what's a semilog plot, and why do we need it? Right? So let's jump back up here to our box. Right? A semilog plot just means that one of our axes is logarithmically scaled. That's a great word, logarithmically. Right? Just means it's base 10. Okay. Now, in statistics, you can scale both axes, all right? But in pre-calculus, we only scale the y. Right. And I just like to kind of write this note so that I have it. Between 1 and 10, we count by ones. Between 10 and 100, we count by tens, okay? So you count by whatever that lowest value is in that interval, okay? So on and so forth. Okay. Now, we're going to talk about the why for this in just a second, all right? But the first thing I want to do is just to practice graphing some points, all right, on this paper, all right? Graphing some points on these papers. Right. So let's look at the first one. Here are 5 points. I want to plot them on this black colored graph paper, all right? Just because it's smaller, we can see it a little better. Because that blue one, there's just so many lines there. My poor little readers can't even help me focus, okay? So let's take a look. We're going to graph some points. Let's look at the first point. A is 120, okay? So 1 is my x value, 20 is my y, okay? So to graph it, it's just like a normal ordered pair, left, right, up, down, okay? Because everything's positive for logarithms. It's all in the first quadrant, okay? So we're going to go right 1 and then up to 20, which means I go to 10, and then one more line. So that would be point A. Okay. Point B is going to be 2, 300. So I'm going to go right 2. I'm going to go up to 100. And then how many more lines do I need? 2 more to get to 300. Yep. Then we have the ordered pair 3, 2. Right? So right 3. 2 is going to be my first little line up. Then we have 4, 15. Now, everything's in tens, so where's 15 going to fall? in between, all right, 10 and 20. So I'd go right 4 and up 10, there's 20, so halfway in between, all right? So it's okay to do that. And then 5, 350. Right 5, up to 300, and halfway, okay? So question about graphing the points. All right, that's a number one thing we got to be able to do. Understand the scale, graph the points. All right, just a new weird graph paper, okay? When we get to polar coordinates, which is coming in Unit 3, it's a circular graph paper, okay? So you're just going to learn all these new graph papers this year, which is kind of cool, okay? I love Kelly Beth's face. Okay. Let's look at the next one, okay? This one we're going to do on the one on the right, okay? We want to graph the line y equals x, okay? And it gives me the values that it wants me to use, okay? So when x is 1, what would y be? 1. When x is 5, y would be 5, okay? When y equals x, okay? So I want you to take a second, and on that blue graph paper, I want you to graph y equals x using those points, okay, that they gave you right there in that bracket. Bless you. Okay. So we should have gotten something that looks kind of like that, all right, give or take a little bit. All right, what do you notice about that? It's a curve, okay? So when I graphed a line, I ended up with a curve, all right? So I'm just going to connect those dots for just a second so we can look at. We ended up with a curve, all right? So when I started with a linear function on the logarithmic paper, I ended with a curve, okay? What would you say about that curve? It's increasing at a decreasing rate. Y'all are getting so good with that. I'm so proud. Okay, it's concave down. All right, so we know that it's a decreasing rate. Okay, interesting. All right, let's do the same thing with example 3. All right, but this time I gave you a little bitty one to use. Okay, and we're going to graph that table. All right, and then we're going to talk about what we see. All right, so here's our picture, give or take a little. All right. What do you notice about this one? It's roughly linear, okay? It appears linear. All right, let's take a second and look at our table. Was our table linear? No, it wasn't, okay? What kind of table you think we got right there? It is exponential, okay? It is exponential, all right? If we look, we could mess with those y values. They are proportional. They're not perfect, but they are proportional, right? And our inputs are changing at a constant by a constant value. So we've got something exponential. So if I start with a line, the log plot gives me a curve. If I start with a curve, it gives me a line, okay? And that's the important part, okay? Because a lot of times it's hard to fit an exponential model. Now, this is an exponential model, but it's been moved around the coordinate plane. So it's harder to know, where did I start, where did I stop? Like, what was there a multiple in front? Is this just 2 to the x minus 7? Or is this 5 times 2 to the x minus 12, right? So if we're not sure, a semi-log plot is a really nice way to be able to say, oh yeah, that table's exponential, okay? So when we look at the next page, when it says, why use a semi-log plot, okay? Why do it? Well, because it's useful in visualizing an exponential function. Okay, it's useful in visualizing an exponential functions. On a log plot, exponential becomes linear. Okay, so some of the multiple choice questions that I've seen that they've released, they give you a log plot, a semi-log plot, and they ask you which model is represented by the log plot, and they give you a bunch of equations. If it's linear, you're going to pick the exponential one. All right, and that's really as tough as it gets. All right, in terms of that. Yes?
Can you say the thing, like, if it's a line, it's exponential, like, that whole thing?
If you start with a line, you're going to get a logarithm, you get a curve. And then if you start with an exponential function, you get a line. Which is kind of cool. So if we weren't sure, we could graph it and see. You can use it. Do it. Okay. I've not graphed a quadratic, so I don't know. That's a good question. I have no idea. The depth of our standard is to recognize exponential on there, so that was as far as I went. That might be something fun to look up. I don't know. Okay. All right. The second thing that we have to talk about, which was our second standard, was a linearization of exponential data. Okay. So what that means is we want to take this exponential function and we want to write it in log form, right? Because it's an equation, right, and we're using base 10, what kind of logarithm should we use? Base 10. Common log, okay? So I'm going to take the log of both sides. So I have the log of y equals the log of a times b to the x. Right. Now, we're going to use our properties of logarithms. I'm really only concerned with that right-hand side. And so a lot of times you'll see them write this side as just y sub 2. All right. I understand that I'm doing the log of everything, but I don't really care about what that looks like over there. All right. I'm just wanting to take that exponential function and put it into something with a log in it. All right. To do so, all right, using our properties, what could I do to separate that a little bit since it's multiplication? I could do the log of a plus the log of, I don't know why I put a down low. Hold on a second. All right, I could do, stop that. All right, the log of a, there I go, plus the log of b to the x. Anything else I could do to it? Put the x out in front. So this would be the log of a plus x times the log of b. Okay, and I put that in parentheses for a purpose. All right, yes, ma'am.
Where did you get the y to again?
They just use that. They say don't worry about that being log y. They say just make it a different variable. Okay, but in order to have equality, I had to take the log of both sides. Okay. All right, so now I want you to look at what we have left. All right, so I've got this equation, y squared equals log a plus x times log b. Remember, log a is a number. Log b is a number. Okay, so what form is this equation now in? Y equals mx plus b, or b plus mx, right? My y-intercept is log a. My slope is log b. Okay? That's the same thing as if you're thinking linear, b plus mx. Right? And I'm going to show you how they're going to ask you a question about that in just a second. Okay. The main thing I need you to see right there for me, okay, is we take the log of both sides. We don't really care about the y side. We just care about the equation itself, okay? What does it become? It becomes linear, right? And you can do that. I need you to be able to recognize that this is linear. What's next to x is my slope. What's by itself is my y-intercept, okay? Now, let's take a look at a couple more examples, right, where they might ask me to do that, right? So let's take a look at this table. And it says, do the values in this table represent an exponential function, yes or no? All right, let's look at it. What do you think? Yes. Here I have an input change of 1, an output change of multiplying by 2. Okay, so we could say yes, the outputs change proportionally while the inputs increase by 1 or are equally spaced. Okay. All right, part B. Let's find the equation of this function. We know it's exponential, all right? We know that its base is going to have to be what? 2, okay? 2 to the x. But what do I need to go in the front? It's not 1. I need that 0 term. What's my intercept? Okay, which means just like when we were doing geometric series, I got to find the 0th term. If I multiply by 2 going forward, what am I going to do to go backwards?
Divide by 2.
Divide by 2. And so what's my first term, or that 0 term, going to be? 0.5 or 1/2. Okay. Now, part C, this is where we want to convert it to linear form. That means we're going to take the log, okay? We're going to take the log. We're really taking the log of the whole thing, all right? But we're not concerned with that left-hand side. So we're just going to call it y2. Okay. So I get log of 1/2 plus log of 2 to the x, which would be the same thing as log of 1/2 plus x times the log of 2. I don't want to mess with that log of 1/2 because I need a number there, okay? How do I know that I'm in linear form? Well, if I can identify the y-intercept and the slope. Okay. What's my y-intercept going to be? Log 1/2. And what's my slope? It's log 2. Yeah, log 2. Okay, whatever's standing next to x is your slope. And that's it in terms of that linearization part. Okay. You could memorize that formula up there in the notes, but to me it's just as easy just to use the log properties. Okay, I don't think that's something you need to add to your treasure trove of memorized things, right? If we can do the properties, we can make it linear. Okay, so that's where I stand with that one. Question on that example? We're almost done. Okay, I want to show you some multiple choice that are similar to what you might see. Some I pulled from AP Classroom, others I pulled from some different places. Okay, let's take a look at this one, example 5. After Mr. Passwater tells another one of his hilarious math jokes, it begins to spread around the school. The number of people P that have heard the joke after T minutes is graphed on a semi-log plot where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for P? Okay. What does our graph look like? It's linear. And if it looks linear, what does my function have to be? Has to be exponential. Okay, which one of those things are exponential? D. Okay, it's not added to, it's going to always be multiplied by. Okay, it's going to always be multiplied by. All right, question on that? Okay. So if our graph is linear, our function will be exponential. I want you to be able to recognize that. All right, let's take a look at this one. Gives me a table. All right. Selected values of our function, which of the following graphs could represent the data in the semi-log plot where the vertical axis is logarithmically scaled. Now, you should be able to eliminate a couple of things before you get very far in the process. Okay, which graphs don't have a logarithmic scale on the left-hand side? A and C. Okay, they just don't have that base 10 logarithmic scale, so don't need to worry about those. Okay, on 10, it has that scale, but only for a little piece. It just goes from 1 to 10. The next one goes from 1 to 1,000. All right, so before you get very far, which one do you think is going to be the right answer? I do think so too. But could you check it? Sure. At 5203, yep, that's it. We could check it. 500, 203, yep, it's D. All right. I really feel like one of your questions will be something like that on the AP exam. Okay. So do you understand what I mean by this is new, but it's doable? Right? I think it's something we could get the question. All right. If we get 2 more, we'll call it done. I'm going to leave you time to practice and start thinking about getting ready for your test on Thursday. This one's really cool. All right. In a semi-log plot, which of the following pairs of functions would appear as parallel lines? What do you think? Okay, they've got to be exponential, right, to be linear on a semi-log plot. So which function should I choose? C. Okay. And the reason why they would be parallel is because of that. If we wrote those in that linearization form, log 2 would be my slope. Okay. And that log 3 would be that horizontal shift, vertical shift that would give me 2 parallel lines. Just a neat way to think about that. Okay. All right, last one. Okay. Lots of math in this problem. Okay. All the different letters. We don't want to read it, but it's really not that terrible. Okay. It says the function f is given by f of x equals a times c to the x, where a is greater than 0 and c is greater than 1. Which of the following is true about the values of constants m and b in the equation ln of f of x equals mx plus b? Okay. Now, what I need you to understand about this problem is that they're talking about a linearization. Now, they didn't use log base 10. What did they use? They used ln. Okay, so here's what I'm going to do. I'm going to take my function. F of x equals ln, equals a times c to the x. Start there first, sorry. And I'm going to do that linearization, that ln. Okay, so I'm going to take the ln of both sides. So ln of f of x equals the ln a times c to the x. So that same thing we've been doing over and over and over. Okay, I'm going to separate it so that I'd have ln, y'all, I can't write today, ln of a plus, and if it's okay with you, I'm going to go ahead and do x times ln of c. All right? So what's my slope? ln of c. And what's my y-intercept? ln of a. Okay? So now I know. I also know that a is greater than 0 and c is greater than 1. All right? They told me that from the get-go. Right? So now let's look at our statement. On the first one, the slope is greater than 0, m is greater than 0, because the natural log of c is greater than 0. All right? Do y'all think that's true? If c is greater than 1 when I started, I've got a number here that's not 1. So the ln of that number would have to be greater than 0 because the ln of 1 is 0. Okay, so that part's true. All right, and b can be any real number because ln of a can be any real number. Well, if a is greater than 0, could b be any real number inside of there? Yeah, it could. Okay, if a is greater than 0, can I take the logarithm of it? Yep, I sure can. So that's going to be any real number. Okay, that whole thing is going to be any real number. The correct answer is A, but I want to talk about why the other things aren't true. Okay, it's nice when the first one's true. All right, but let's look at the rest. It says m is greater than 0 because the ln of c is greater than 0. Well, that's true. Okay, but that b has to be greater than 0 because ln of a is greater than 0. Well, let me ask you this. If the ln of a, all right, or if b has to be greater than 0, what if a was 1 over 36? What would be the natural log of 1 over 36? Would it be positive or negative? It would be negative, okay? So 1 over 36 fits the bill for a greater than 0, but it does not make my logarithm greater than 0. Does that make sense? You got to think about all of that. So it can't be this because of that one. Right. The next one, it says that my slope can be any real number because the ln of c can be any real number. Well, we've already established that's not true. All right, ln of c has to be greater than 0. All right, because c was greater than 1. And then on the last one, same thing. m can be any real number because ln of c can be any real number. That goes ahead and cancels it out before we think about the rest of it. Okay, that's a tough AP kind of question. It would show up on a calculator section. Don't ask me why. Okay, they like to put a lot of the theory in the calculator section. I don't know if that's so you can play with it a little bit, looking at a graph, put some numbers in and think about it. But they do like to put a lot of their theory questions in the calculator section. But I don't really need a calculator for that one. Okay? All right, so that's that. All right, that's semi-log plots. Questions? Yes, you may. Okay. All right. So your worksheet tonight has, I think, 11 questions. We're not going to do them all. All right. We're going to do 1 through 7 and then number 10. All right. Now, you've got a lot of time today, all right, more than usual. So let's don't just socialize for 35, 40 minutes. Okay, let's use this time to practice, to work on your AP classroom questions. Okay, we're going to do review tomorrow. Be sure you have your iPad charts when you come in tomorrow. There's a survey we have to do, and tomorrow's our day to do it. Okay, so we'll do that at the very beginning, and then we will get into your review and stuff for your test. Okay, test Thursday, corrections Friday. All right, I know there's some field trips I've signed and things. Okay, so you'll just, we'll just make it work. All right, when you get back. Okay. All right, there you go. Got it good.